Swayam Prabha. Digital India. Educated India.
The next presentation is the Dr. Aditya Swami. I'm not sure of the pronunciation. He's online. Can you hear me?
Hi, yes. Am I audible?
Okay. So please share your slide.
Yes, sir. Hi, is the screen out for everyone?
Yes.
Yes, okay. Well, good afternoon, everyone, and welcome to PSC Asia 2022. My name is Aditya Swami. The topic for this panel is AI for complex systems, and this is the paper I'd like to discuss with you. Interpretable machine learning models for prediction of fuel properties. This is something that myself and Shashank Sisla worked on at the Department of Chemical Engineering, Pilani, Hyderabad campus. We did so under the guidance of Professor Arnab Datta and Professor Ayman Abrar. Now, before we get into the what of what we did, I'd just like to take a minute and talk about the why. We live in a world where resources are ever depleting and computational power and data sets are ever increasing. So it's only natural that the world tends to make a switch towards modeling and simulation-oriented processes. Sustainability is, of course, a very real consideration given how climate change is accelerating. And we see applications of AI in many such instances. Optimizing power grids, optimizing appliances, etc., heat exchanger networks. There's a variety of these, and the application we focus on is characterization and screening. What we aim to do here is to produce a model to predict fuel properties with one important consideration that many projects often overlook, and that is interpretability. Interpretability is understanding why the model is behaving in the way that it is behaving. This helps not only on the back end, the debugging, but it also helps the users gain faith in the model and understand the behavior of the model and the output that is producing. So, what is it that we did? Well, we built a model using the group contribution theory by the University of Birmingham, and we trained 3 different models. We were using these to predict 3 different properties of fuels and fuel mixtures. The properties we were predicting were the cetane number, the research octane number, and the motor octane number. The cetane number is an indicator of the combustion of the speed of combustion of diesel fuel. It is more specifically an indicator of how quickly the fuel can combust when being introduced to the spark plug. The octane numbers, on the other hand, are representative of the resistance of the fuel to pre-combustion due to compression before they actually meet the spark plug. Once our models were built, we interpreted them using SHAP analysis, or shapely additive explanations, which we'll talk about later in the presentation. So, coming to the dataset and the metrics that we used, we had 3 different models, and for these we had 3 different datasets. The datasets for cetane number, research octane number, and motor octane number had 32 features each, which we used to train the model, and they had 603, 374, and 371 entries respectively. For these models, we use the R-square metric to validate them. The R-square metric is a goodness of fit metric. It tells us what part of the variance of the model's output is actually by the model output and what part of it is just noise. A perfect model, an ideal model, would have an R-square value of 1 or 100%. For our models, all 3 of them, we used boosted ensemble methods, more specifically extreme gradient boosting or XGBoost. XGBoost is an algorithm that's been around for 4 or 5 years now. Until around 2015 or 2014 is when it was first publicized. And it is an extremely efficient and accurate method of boosted trees that allowed us to get an overall R-square of higher than 99%. Now, the competition here was a Gaussian process regression, which is another non-ensemble method of predicting properties. And the R-square that we were getting on the entire data set was comparable to that of the GPR. However, one consideration is that the GPR was not tested on unseen data. For this, we wanted to draw an apples-to-apples comparison And for that, we use 10-fold cross-validation testing along with random search CV, which we'll talk about in just a minute. What we wanted to do is ensure that the model is not only able to predict fuel properties effectively on the data set that we have, but we also wanted to make it scalable for unseen fuels and unseen mixtures. For this, we had to test it on unseen data. The cross-validation method that we followed was an iterative 10-fold cross-validation. So, what we were doing here is splitting the overall data set into training and testing data. The training data was then split into 10 folds, although the example here says 5, but we used a 10-fold validation. Each of these 10 folds is then considered to be the holdout set or the testing set, and the model is trained on the remaining 9 folds, and then tested on the 10th fold. Due to this, each iteration of this produces 10 models, and we had 10 iterations. So we had a total of 100 models, which were all then tested on the validation data which we held out at the beginning. The mesh model from these was selected. And given the size and the complexity of the hyperparameters that are present in an XGBoost model, we used a random search instead of a grid search, which would be far more computationally heavy. Using this method, we arrived at our final model that was giving us the highest R-square value. Now, the data set had a variety of different organic compounds and fuels, and we wanted to ensure that the model was equally adept at predicting properties of all of them. Hence, we stratified the testing and the training data set on the category of organic compound, and then validated the test scores on unseen data. Serial number data set was the highest accuracy, as you can see in front of you, and although I must say that all of the models were performing really high with R-squares of over 80%. Now, the models were built and they were done predicting, and we tuned them and we got the best output possible. The next step was to interpret them and to understand why the models were behaving in the way that they were behaving. For this, we used SHAP analysis, or shapely additive explanations. SHAP analysis is a game theory-based approach which uses shapely values to gauge feature importance. An important consideration and a big part of why we chose the SHAP analysis is because this library in Python, or even SHAP analysis as a concept, is model agnostic. This means that it can be used to interpret any category of model, be it boosted ensembles, be it neural networks, or even a simple linear regression. Another additional feature of this is that it can be used for both global and local interpretation, unlike its competitors, which we will also discuss in the next slide. The downside to this, however, is that the highly accurate output is computationally heavy, and pretty often it took us longer to interpret the model than to actually train it. So, a quick comparison. LIME, or local interpretable model agnostic explanations, is another popular method of interpreting models that we saw in literature. The reason the table you see in front of you draws the drivers as to why we chose SHAP over LIME. SHAP uses game theory-based explanations to understand the model's behavior, whereas LIME uses a sparse model. What this does is it takes a singular point and tries to generate a linear curve around it in the same way that the actual model would have. With this, it tries to fit a linear regression around those points and get an understanding or feature importance from that linear regression. Now, the downside to this is that it can only be used for one instance at a time, and thus LIME only provides local interpretation. SHAP, on the other hand, can provide us both global and local interpretations, but the downside to this, as we discussed earlier, is that LIME is often much faster than SHAP. Another consideration that we had in mind was that the visualization of the interpretation is extremely important when presenting our case. So, this is another advantage of the SHAP library in Python, and this is more specific to the library itself rather than the concept. But SHAP gives us a variety of visualizations, both global and local, and the ones provided by LIME are usually not as engaging. So, a few examples of these. We first look at global explanations provided by SHAP. What you see in front is the feature importance from our CK number model, and this plot is called a B-swarm plot. So each dot here represents an instance in the testing data set, and the density of this plot, or the density of the dots, either on the left or the right of the line, indicate how much of feature importance that variable holds for the model's output. A higher value, of course, indicates a higher Shapley value, which in turn indicates a higher impact on the model output. A positive sharp value will indicate a direct correlation between the model output and the feature value. So if the feature value is higher, the model output will be higher. This is applicable in our case because we have a continuous output, but in the case of a logistic regression, the explanation changes slightly. There are other ways of visualizing this, one of which is a Weiland plot, which is nothing but a smoothened version of the B-swarm plot you see in front of you. And the other one is a bar plot, which simply plots the absolute sharp value in terms of histogram as a bar plot. The other kind of explanation that SHAP offers are local interpretations. What you see here is a force plot, which is a very interactive and engaging way of explaining which features are the drivers of the model output and which features actually lead to a higher continuous output and which features lead to a lower continuous output. A fun fact here is that these plots are actually interactable if you generate them in Jupyter notebooks in the HTML wrapper that they provide. So you can zoom in and get higher or lower number of features. The two explanations that you see here are menthone and N-hexadecane. The red features are those driving the continuous output higher, and the features marked in blue are those that drive the model output lower. The base value indicator can be thought of as an intercept, similar to that of a linear regression. And as you can see, the predicted numbers are actually pretty close to the true value of the numbers. Now, the conclusion to all our work, the product that we talked about at the beginning. Once we were done building our models and gaining insights from their interpretation, what we wanted to do is allow others to use our work for free and effectively. For this, we built a graphical user interface in the form of a web app. This tool was published on Heroku, and has been on Heroku for the last few months, but as of December 22, Heroku has shifted from a free subscription to a paid subscription, so we are in the process of setting that back up. But the web app is based on HTML for the front end and a Python library called Flask for the back end. With this, you can input up to 4 different compounds and their mass percentages in a mixture. And all you need to do is input the IUPAC name along with the mass percentage. Error handling and feature extraction are completely automated. And as you can see from the screenshot in front of you, you get the predicted 3 numbers that we were talking about for this paper. For our feature extraction, and this is an important consideration for us because not only did we want to be able to predict accurately like we discussed, but we also wanted other people in various fields, in academia included, to be able to characterize and get the predictions for mixtures that have not been seen before. For this, we used the following pipeline that you see in front of you. Once the user inputs the IUPAC names of the compounds first and the mass percentages, the first set is the error checking to make sure that the IUPAC names are accurate and that the mass percentages all add up to 100. If all is in order, then we use a library called pubchem.py, another Python module. And we use this to get the SMILES denotation of organic compounds. SMILES is nothing but a way of representing organic molecules as strings in a programming language. So, for example, if you had a carbon single bonded with another carbon, you would represent that as a C-C. A double bond would be represented as C minus C, and a triple bond would be represented as C equal to C. Once we have this pubchem.py SMILES denotation for the input mixture or the input IUPAC names that are provided, we use a library called rdkit for their visualization and feature formation. As we discussed earlier, our dataset had 32 different features, and using RDKit, we developed functions to automatically extract these features for all organic compounds that the user has provided. For a mixture, the features would be nothing but the weighted average of the features for the independent compounds. So once we have the feature matrix for up to four independent compounds, we then take the weighted average based on the mass percentage and get the 32 feature matrix for the overall input. This is then passed to our pre-trained models that we have already discussed, and the output is finally provided to us. That's all for my presentation. I'd like to thank PSE Asia, IIT Madras, IIT Bombay, and BITS Hyderabad campus for all their help with this. And just before we sign off, I'd like to take a minute and have a quick demonstration of the GUI that we were talking about. Yeah, is the screen up for everyone? Yeah, sorry, I was having a bit of technical issue. So this right here is what you see in front of you. This is the fuel property prediction tool. Here we can take various inputs. Let's take N-heptane, isooctane, toluene, and cyclopentane in a simple ratio of 25% each. Yeah, and there you have it. The output comes up right there. So the error handling is also inbuilt to it. For example, if I was to type in an invalid IUPAC name with the correct percentage, I would get the relevant error for this. And if I was to type in, say, this with 110, which doesn't work, we get an invalid fuel composition error. So that is the GUI we developed, and I hope this presentation was fun for everybody. If there are any questions, I'll be more than happy to answer them.
Okay, thank you. Two questions. Are there any questions? Okay.
So I see you use CHAP here. So one of the things that is always needed when you provide any explanation is you need to get an expert into the loop, where someone who knows the domain very well needs to evaluate these explanations, and then again you need to see if your model is based on the correct factors. So is there anything that you've done similar to that?
Yes, so that is where Shashank Sisla and myself took the guidance of Professor Abhinav Datta and Professor Ayman Abrar from our campus for this. The models have been built and we are still undergoing literature review to get the insights, as they are the experts in the field.
Okay, so let's move to the next presentation. Thank you very much.
Thank you, everyone.